Okay, so today I'm going to discuss an important question. Okay, many students have doubt in this question, so I thought that I should make a video uh, and try to explain. Okay, so the question says that does there exist a monotone function such that set of discontinuities is exactly Q? The meaning of the question says that does there exist a monotone function such that it is discontinuous at each rational point and continuous outside. That means continuous on each irrational point and discontinuous at each rational point. And also the function is monotone. Is it possible? So before going to solve this exact problem, first let me explain that everything details about monotone function. Okay. So the theorem: any monotone function can have at most countable many discontinuity. Okay, it's proof. So without loss of generality, I am assuming that our function is monotonically increasing. You can do the same thing for monotonically decreasing. Okay, without loss of generality, assume f is monotone increasing. Okay, then my claim is that f can have at most countable many discontinuity. Okay, so let f is discontinuous at some point a. So we know that f of a minus less equal to f of a less equal to f of a plus, because f is monotonically increasing, right? So since f is monotonically increasing, so that means f of a minus less equal to f a less equal to f of a plus, right? So if f is discontinuous at point a, that will imply that f of a minus strictly less than f of a plus. Mind it, my function is monotonically increasing and it is discontinuous. So that means discontinuity is just like this, right? Say it is discontinuous at this point. So the function can behave like this and then that, or the function can behave like, say it can have left hand limit but not the right hand limit, right? Or it can have right hand limit, okay? Say it can have right hand limit but not the left hand limit. So ultimately the conclusion is this one, right? So that means since f is discontinuous at point a, that means f of a minus less equal to f a less equal to f of a plus. So since f is discontinuous, that means f of a minus is strictly less than f of a plus, because if that is both are equal, that means f becomes continuous, right? Because f is monotone given, right? Okay, fine. So now that means this gives you an interval, right? This gives you an interval, right? Now you can choose a rational number from here or from this interval, right? You can choose a rational number from this interval. Rational number, because rational number is dense in real number, right? So whenever you are considering any interval, you can always choose a rational number in this way, right? Now say a not equal to b two distinct element such that f is discontinuous. Okay, two distinct elements such that f is discontinuous. Then clearly f of a minus less than f of a plus, since f is discontinuous at a, less equal to f of b minus less than f of b plus, right? That means this one is an interval and this one is an interval. So say this one is this interval and this one is this one. This is a different interval, right? So you can always find some rational number, say uh, r suffix a and some rational number r suffix b, such that Ra not equal to Rb. You can always choose, right? And that everything happens because of f is monotone increasing. Okay, mind it. This is very very important that f is monotone increasing. So that's why you can choose this kind of element, right? So from here, what you have, what you have got. So let d equal to set of discontinuities of f. Okay, and consider a map phi from d to rational number where a goes to Ra, where Ra belongs to that fa minus comma fa plus, this interval. You can always define this map, and this map is 1 1. Why? Because you can always find such a such that this one is not equal to this one. You can always find. So that means you can map it injectively. So if a not equal to b here, you can always find Ra not equal to Rb here. Okay, so that means it is injective map. Right? This will imply D is countable. Because image is q, right? Image may not be whole q. Set of discontinuous may not be whole q, but that can have a bijection, that can have a, like, you have an injective map from d to q. Okay, so that means cardinality of d less equal to cardinality of q, and q is countable, hence d is countable. This is the proof that uh, any monotone function can have at most countable many discontinuity. Okay, now the question, now come to a different question. Let a be a subset of real number such that a is countable, right? Can we construct, I'm something asking about the converts. So the most of the important good exam like DIFR, NBHM, and also many interview, this same question asked. Okay, in many interview, even in case of me, in some interview, this type of question asked. Okay, so let a subset of R such that a is countable. Can we construct a function f from R to R such that set of discontinuities, that means the points where f is discontinuous, f is a. Okay, that means outside a it is continuous, on a it is discontinuous. Can we make it? See, so if a is finite, you can easily make it. There is no issue. But I am talking about a is countable. That means a can be set of integers, a can be set of natural numbers, a can be set of rational numbers also, which is dense integer. That is the question. Actual question, that does there exist a monotone function f such that set of discontinuities construct a function and also it is monotone function a such that R2R such a set of discontinuities of a is a. If I can make it for any countable set a, that means in particular if I can choose a to be q, then we are done also, right? So let's do that. So that means we need to construct such function such that this property holds, right? Okay. Let A be the given countable set. So since A is countable, we can write A as x1, x2, x3 and so on. It could be finite, it could be infinite. That is not an issue. Okay, that is not an issue. But we can write it in this way. Basically, we can enumerate A, right? We can count the element of A because A is countable. So we can write it A as x1, x2, x3. So it could be finite, but it is at most it is countable given. So we can write it in this way. Now define a function R2R. Okay. Define a function R2R. F of x is summation 1 by 2 to the power n such that xn less equal to x. See, I am considering a function fx equal to summation 1 by 2 to the power n such that xn less equal to x. See, summation 1 by 2 to the power n is a convergence series, right? That means this is a finite sum. So the function is well defined, there is no issue. Now we need to check the property which we are finding that this function satisfies or not. Okay, that is important. So check f is monotone. How can I check? So I'm in particular make this function as monotone increasing function. Okay, so let x less than y. So this should imply that fx less than f1, less equal to f1. Okay, I'm not considering strictly monotone, that is not possible. Okay, I'm considering just monotone, so it may be equal or less than. Okay, fine. So fy minus fx is basically summation xn less equal to y 1 by 2 to the power n minus summation xn less equal to x 1 by 2 to the power n. Now x is less than y. That means there might be some xn which is inside the interval x comma y. But all the xn, but we can see all xn less equal to x imply xn less equal to y. That means xn contribute in this sum as well as that xn must contribute in this sum also, right? So what we'll have? We are getting x less than xn less equal to y 1 by 2 to the power n. So that may be 0, because if there is no xn inside the interval x and y, then it's definitely this quantity is 0. But if there is some xn, then this quantity is positive. That means it is greater equal to 0, right? Which implies f of y greater equal to f of x. It implies f is monotone, right? Fine. Now what we need to show? We need to show that f is discontinuous at every point of a, right? Because we are given this set and we are trying to construct a function f which is monotone increasing, and it has discontinuity at every point of a, right? And everywhere else it is continuous. Okay, check f is discontinuous at a. f of a is basically summation 1 by 2 to the power n xn less equal to a. F of a minus must be summation xn strictly less than a 1 by 2 to the power n. Okay, but see, since a inside this countable set and we are enumerating this, so that means a must be inside this sequence xn. Okay, that will imply this must be strictly less than summation xn less equal to a 1 by 2 to the power n, because this is same as summation 1 by 2 power n xn less than a plus summation plus 1 by 2 to the power n where xn equal to a. That means for xn equal to a, this extra term contributes, which implies that f of a is strictly greater than f of a minus. So that means if you are choosing any point x which is less than a, strictly less than a, that means this sum must be strictly less than this sum, because here a is inside that set itself. So for other case this term may not be contribute because they are, but in this case it contributes because xn equal to a is already a term here. A is inside this sequence xn. We are enumerating this, right? What is xn? See, what is xn? Xn is this, right? So since a belongs to xn, so there is some n for that xn equal to that a, right? So this sum, that means xn contributes in this sum. So f is greater than f of a minus, which will imply that f is discontinuous. F is discontinuous. Now only thing left is to check that f is continuous outside. Must say. How can I do that? Let's think it geometrically. Okay, let's think it geometrically. Draw a line. Okay, say you have this point, not a, I am going to give it say y, right? So from the definition, say f of y is some value here, right? That means f of minus y is some value near about this, right? Because this is monotone increasing, it is obvious. And f of y plus is some value here. We need to find that this is actually same, right? Because we need to check that f is continuous, right? So observe that so what we need to check, we need to check that f of y minus is equal to f of y is equal to f of y plus, right? So let's see. So we need to check this should hold, right? This should hold. And we have, since f is by construction f is increasing, so that means this already holds. Right? This already holds. Now, if this is discontinuous, that means either this or this must happen, right? If it is discontinuous, either this or this must happen. So let's first consider this case f of a greater than f of a minus. What is f of a? F of a means xn less equal to a 1 by 2 to the power n, right? This is strictly greater than summation xn less than a 1 by 2 to the power n. So it is strictly, so here the inequality is strict. So from here you can conclude that xn equal to a for some n, right? Because in this sum we are taking xn less equal to a, In this sum we are taking xn is strictly less than a. If this sum is strictly less than this sum, that means there must be some n such that xn equal to a, so that there is some 1 by 2 power n which contributes in this sum that doesn't contribute in this sum. That's why this sum becomes strictly greater than that sum, right? So which implies that xn equal to a. But that is contradiction to our assumption, because we already assumed that x. Oh, okay. We are taking it to y, right? Okay, let's take it here. There's no issue. That gives me a contradiction. Similarly, if this happens, that means what? Xn less equal to a plus. I'm choosing a plus means that is any real number that is greater than a. Okay, it is xn or n is equal to a. See, here it is, we need to find out some epsilon so that this is happened, right? So from here we can conclude that xn must be a for some a. Why? Because here it is, you are taking some a comma a plus epsilon, which you are denoting by a plus, right? Which you are denoting by a plus. So if this sum is strictly greater than summation 1 by 2 power n, okay, that means for some a plus, xn equal to that a plus that is inside that a, but you can choose arbitrarily a small epsilon, right? Epsilon is arbitrary. Here epsilon is arbitrary. That means you can make it as small as you want. You can make it as small as you want. So say say for each epsilon n this happens, right? For each epsilon n you are finding some an such that f of n strictly greater than f of a. Say you are considering, because you can choose epsilon to be anything, and for each thing you that there might be some n which is strictly greater than a such that this holds, right? But epsilon, since epsilon is arbitrary, that will imply n tends to a, right? And which will imply this sum must be equal to this sum. This sum must be equal to this sum. Okay, it is pretty obvious, right? Because so it's slightly difficult to understand for this, but I think you will understand if you if you visualize it graphically, right? So what I am taking in this sum, we are taking that, so this sum is defined for any a greater than any x greater than a. So I am taking some small neighborhood of a. That means I am considering that x which is epsilon greater than a. Okay, but that epsilon is arbitrary. I can choose whatever I want, because I am considering here it's a continuity. I am checking it continuity, right? So that means I can choose whatever I want, whatever epsilon I can want. But in that case, I can always find a sequence an such that an converges to a, and for each an this sum greater than strictly greater than that. But which is a contradiction, because an tends to a. I am considering xn less equal to a plus. That means ultimately this sum goes to, that means since an tends to a, that means this sum xn less equal to an 1 by 2n, this goes to summation 1 by 2n xn less equal to a, because this is the convergence series and this is the property, that will imply that this must be equal to that cannot be strictly greater than this. Okay, I hope this idea is clear. If you have any doubt, you can comment. Okay, but this is an extremely important question. So that means for each a, which is countable, I can construct such a function. So in particular, you can choose a to be q. Sorry, I write it later. So in particular, choose a to be q and construct such function. Okay, thank you.